So in the lab on Monday, you are going to be not only building batteries that have different elements in them, but you'll also be building a battery that has just the same element on both sides. But it will still run because it has a difference in concentration in one half cell versus the other. It's going to be a concentration cell. All the math related to that comes from the Nernst equation. What you've been doing is calculating E standard for cells. Standard means generally at 25 degrees Celsius, and when the concentrations of aqueous solutions are 1 molar and the pressures of gases are 1 atmosphere. But in our concentration cell, we will not have those standard conditions because we have different molarities in both of the half cells. And so we'll be calculating just the non-standard E value. That is what we use when we don't have 1 molar or 1 atmosphere for reactants or products. So, E is going to be equal to E standard minus 0.0257 over N times ln of Q. So what is Q? That's the reaction quotient. We learned it back in about February. Q is equal to the amount of product over reactant, right now. The concentrations of products over reactant. And of course it has coefficients. So let's say that, there were 2 products formed, then you would have squared. And then let's say there were 3 reactants needed, then you would have cubed, etc. Let's go ahead and see how to use this equation for a concentration cell where we have silver as the electrode in both half cells, but in the left half cell we have 0.2 molar silver nitrate solution, and in the right half cell we have 1.0 molar silver nitrate solution. So, which way are electrons going to transfer, and is the concentration of this silver solution is going to increase or decrease, and will this one increase or decrease? So, you can kind of think of having different amounts of water on both sides of a bucket. If you have more water on the right side than the left side, water is going to flow from high altitude to low altitude until you'll have equal heights or altitudes, heights of water on both sides. And so it's going to be similar with this case. We're going to have a flowing of electrons so that the concentration of silver ions in the more concentrated solution decreases. And the concentration of the silver ions in the less concentrated solution will increase until eventually you get the same molarity of silver ions in both cases. So there's 2 half reactions that occur. In one, the silver ions are reduced and turned into solid silver. And then in the other, silver solid is turned into silver ions and it's oxidized. It releases electrons. And we want to predict that we're going to be losing some of the silver ions in the more concentrated solution, and we're going to be producing silver ions in the less concentrated solution. Which way are electrons going to flow? They're going to be released from the half cell where you have the less concentrated silver. And then they'll be absorbed, electrons are a reactant, in the half cell where you have the more concentrated silver. So electrons are going to flow from left to the right in this case, towards where the silver is being reduced. Electrons flow to where the thing is being reduced. All right, so having these 2 half reactions, we're going to have an overall chemical equation, but we can simplify it. We know one electron is on both sides and solid silver is on both sides. So essentially, silver ions that are in the more concentrated solution are going to turn into silver ions in the less concentrated solution. Now, having that, let's determine the voltage that we can expect from this cell. Using the Nernst equation, we can first plug in the voltage that we would expect when we had 1 molar of both ions of silver. Well then, you would be using the exact same reduction potentials for each thing. I'm trying to recall from the reduction potential chart, but it might be around 1.5 or so. But if you did 1.5 minus 1.5, cathode minus anode, you would get 0.00. If you have the same elements in both of the half cells, then the standard reduction, actually the standard E cell is going to be 0.00. All right, and so then we're going to subtract 0.0257 over n. So n is going to be equal to 1. We can see that here. Only 1 electron is absorbed and released. And then we want to plug in for ln of Q. Remember, Q is the relative concentration of products over reactants. And of course, you don't include solids in that. In this balanced chemical equation, the product is in the 0.2 molar solution, and the reactant is in the 1.0 molar solution. So you have the products in the more dilute or 0.2 molar solution, and you have the reactants in the more concentrated or 1.0 molar solution. So then you can take the natural log of 0.2 and then multiply by 0.0257 and then divide by 1. And that's negative 0.0413 volts, but subtract that from 0.00, and you get that you can expect a 0.0413 voltage from this concentration cell. So this Nernst equation maybe should make some sense to you. If you had 1 molar zinc and 1 molar copper in 2 half cells, you might expect a certain voltage for that cell. But the cell is not going to run forever. If you put a battery in a Game Boy or a cell phone, the battery doesn't last forever. It will not produce that voltage which drives electrons through that device, powering the device forever. The battery will drain. So eventually, the voltage of the cell will fall to 0. And that is because the ratio of products to reactants will change. As you get more products and you start using up the reactants, the voltage of the cell is going to drop until it eventually is not high enough to power the cell. All right, that's pretty much it. Thanks for watching.